Hey, what's up, guys? Okay, so in this video, that I'm gonna to prove the golden Thompson inequality. Golden Thompson uh, Thompson inequality. No, sorry, I misspelled. Okay, inequality. Okay, so this inequality is like very I guess very sophisticated, and proof is not easy to find online. But so I would this is why I want to make a video. Okay, so let me just say the theorem. So theorem just say that if A and B are basically n by n Hermitian with complex coefficient, and then we always have something, right? We have something like so the inequality says this. Okay, take a trace. Okay, trace. Okay, so notice that you can say this is inequality, and there is another equality that I recently proved in the last video, but there's a mistake. So it's basically determinant is exponential a plus b. It's basically same as determinant of. Okay. So this one is simple. Let me just quickly say the reason is that this one, which I proved last time, is incorrect. Basically, you can write this. You can use the BCH formula. Write as this. Basically, so it's exponential a plus b, so a and a b, and the exponential half of ab, and then there's some higher order term. But basically, all the higher order terms are basically in form of commutator, right? So basically, sometimes something like this, or the kind of commutator. And once you take determinants, then basically this can spread, right? This is homomorphism. And you can also use determinant of exponential x. Basically, it's the same as exponential trace of x, right? So if this x is form a commutator, then trace will be 0. So basically, this will just be 1, and all higher than will be 1. So you can easily prove this. So this one is very simple. And but the difficulty is this one, right? This one is maybe not easy to see. And notice that things AB are complex, right? So you might worry that maybe the left hand side or right hand side are basically complex number. But this is not true because it's trace, right? So if A and B are Hermitian, right? Say if A and B are Hermitian, then basically the trace A must be real, right? And so basically these are real, these are both real, which you can directly prove it. So left hand side is real, right hand side is real, so this is why this inequality makes sense. Okay, so prove this, we need a significant amount of work to prove this. So usually when people write proof, right, there are two kinds of proof. One is so-called bottom up, the bottom up, and also top down, right? So bottom up, basically you don't know the detail, you don't know the high level idea. Just somebody just start from somewhere and just tell me step by step, and then you finally get your results. And then another is top down. Top down just I will tell you the step by step and high level idea, so that you can you know what I'm gonna do. Okay, so this proof is difficult. So let's use top down idea. Okay. Okay, so my claim, let me just write down some definition. Okay, in order to do this, let's introduce this shatter norm. Okay, so shatter norm is basically for A and P, and so let's say P is 2, 4, 6. So these P are even. Okay. So this A and P, AP norm divided by the trace of A dagger. Let's say A is general matrices, complex matrices, and go to P over 2, and then you just 1 over P. Okay, so when A is Hermitian, this is easy to see, just trace of AP AB and is 1 over P. So this. Okay, and also the standard one is A2, right? So A2 just trace of let's say A squared. Okay. Okay, so when it's Hermitian. So in general, you can define inner product, right? So this is the Frobenius inner product, basically given AB as complex matrices. You can define trace of AB dagger. I think most of people know this. So this is called the Frobenius of matrices. And sorry, Frobenius inner product. Okay, so the fact is that these guys are basically the valid inner products. Okay. Okay. So what we're gonna say is, right, so this will give you some equality, basically called the Cauchy-Schwarz. Okay. So the Cauchy-Schwarz tell you that the trace of A1, A2 dagger. So now when I don't say it, I mean general matrices, but when I say something, I will just when I focus on Hermitian matrices, I will just tell you. So for general matrices, the trace A1, A2 dagger, that it's easy to see that just using the Cauchy-Schwarz, right? Because it's valid in the products, so it's basically A1 2 norm and A2 is 2 norm. Okay. Okay. So what I'm going to say is the following. So remember this one. Okay. And so this one is general matrices, right? But when A2 is Hermitian, that we can ignore this dagger, right? So basically we have to follow the trace of A1, A2, A1, A2. Okay, so this one is basically simple Cauchy-Schwarz. Okay, so my claim is that there is another theorem. Basically, it's the Holder inequality. For general, basically generalize this into P form. Okay, so what this says that there's a trace A1, A2 up to AP. If all these are Hermitian matrices, then this will bounded by A1 P norm, A2 P norm, AP P norm when P is 2, 4, 8, 16. Okay, so this is called Holder inequality. Okay, so the claim is that Holder inequality, this non-commutative Holder inequality implies golden Thompson inequality. Okay, so the proof strategy is that I first prove this is true. Proof golden equality. This Holder inequality implies golden Thompson inequality. Once I prove this, then I prove that Holder inequality is true. Because proof Holder inequality is true require more work. Okay, so this one I will show that I will just doing this. So I will show first show this is true. Okay. So the step one. Step one, and the step two, I will just show Holder inequality. Okay, so this is the proof strategy. Okay, and okay, so let's do the proof, right? So the proof basically say that your Holder inequality tell you the A1 up to AP, right, is basically bounded by A1 P APP. Where the P is 2, 4, 8, 16. Okay, so you can just first that A1 to be A1, A2, A1, A2, A3 up to is equals to AP is defined to be A times B. Given any two matrices, let's say A and B. Okay, so this immediately give you that trace of. By the way, all these are positive, right? So all these are positive. So if there's sorry. Okay. So if basically they are all positive, right? They are all positive. So the left hand side, the left hand side is absolute value doesn't matter, right? So this gives you the trace of a b to the power p is less or equal to a b to the p norm and go to power p. Okay. Okay. So now here's the trick that you just write down definition, right? So let's maybe do case by case. Okay. So if AB is 2 and 2, so what this means is something, right? This is basically tell you that this is square, right? So you don't care about square. So basically trace of AB. And notice that we need to do AB dagger, right? By definition. Okay. And this is trace of AB. So notice that they are all Hermitian. So basically it's AB squared A. So which is trace of A squared B squared. Okay. If you do AB to the P 4 norm and then go to power 4, you get trace of AB. Right. So by definition, you need to do AB squared A and then go to square, which is a trace of AB squared A and AB squared A. Okay. So you get AB. You get this, right? So notice, and these two can combine, right? So use the cyclic property. So this gives you a trace of right. So this gives you the A square, B square, A square, B square. Okay, so which is just very simple, just trace of A square, B square, and a square. Okay, so you can see that yeah, this is basically what you get, right? So AB 22, AB 44 is basically A square, B square, square, and AB 22 is A trace of A square, B square. Okay, so I think you can just easily prove by yourself that basically you have the following. Basically, if you are doing like A, B, like P, P, if you get trace of A square, B square, P. Okay, so what we have shown is basically trace of the previous Holder inequality become the following. So if AB to a P is bounded by trace of A square, B square to a power P. Okay. Okay, so now we need to do the following. Okay. That's where P divided by 2. P divided by 2. Right, if P is 2, that the A squared, B squared, and then if P is 4, is A squared, B squared, squared. So P divided by 2. Okay. So what this means something, right? This means something. This means that this inequality can actually return as another one. Okay. Return as so let me just write down. So this one implies the following. It implies that trace of A, B to the P is bounded by trace of A to the P, B to the P. Okay. And the reason is that you can keep iterating this inequality. Okay, maybe it's hard to understand. So let me just do a very simple example. Right. So for example, let's say if I want to compute, say trace of AB square, right? By the previous inequality, tell me the trace of A square, B square. Yeah, which is exactly this one, right? Fine. Okay. If I want to compute trace of AB to the fourth, then I can say that, oh, this is just trace of like A squared, B squared, squared, right? By using this inequality, right? But then I can replace this A squared, B squared, squared to be this one. So I can replace A to be A squared and B to be B squared, right? So I can replace it. I got the trace of A to the fourth, B to the fourth by using this. right? So I can use the previous inequality and then replace this a to be a squared, b squared, and then be a to the fourth, b to the fourth. So I get ab to the power first. Basically, that's equal to trace of a to the first, b to the first. So you can keep iterating the previous inequality, and then you finally arrive here. You finally arrive here. So trace ab to the power p is that's equal to trace a to the p, b to the p. Okay. So once we have this, then the rest is basically simple, right? So basically you have trace a to the p, b to the ab to the p is less or equal to trace a to the p, b to the p. For p is the power of 2. Okay, so now you can replace a to be exponential a divided by p. Hopefully this is obvious. B to be exponential b divided by p. Okay, so now your right hand side becomes trace of exponential a, exponential b, and the left hand side becomes trace of EAP, EBP, take power of P. Okay, and this is true for every P, right? So just take P to be infinite. So take P to infinite. And the left hand side something is something. Sorry, so limit P goes to infinity, exponential A divided by P, exponential B divided by P to the power P. It's just this, exponential A plus B. Okay, so this is famous Lie product formula. Okay, so if you if you don't know how to prove it, that I will post my link below. Basically, you can use matrix log or some kind of. Basically, one idea is that you can just expand the title expansion, and then so learn neglecting terms like 1 over p squared. And you do power of p, then this will be small if you take p to be infinite. So this is true, right? So this is true for every p. So if you take p to be infinite, this must also be true. So the left hand side now becomes exponential a plus b. So trace of exponential a plus b is less equal to trace of exponential a times exponential b. Okay. Okay, so this is the proof. Okay. Okay, so in the next video that we will go back to prove this. We will go back to prove this Holder inequality. Right. So this one will take more time. So this video let's just prove half. Okay. See you next videos.